take a moment to introduce the next group, and this group is a little bit out of the ordinary because over the, if I can get everyone's attention, please, thank you. Over October, November, a number of us faculty and a large number of students from sophomores all the way up to the gentleman you see before you hear seniors, worked on a very large NASA proposal, and this they will tell you more about it. But the NASA concept is to underwrite the construction and delivery into orbit of student-built satellites, and these are small little satellites. A number of flights have already gone up, and we as an institution are competing for those grants. That means that this program is a little different from the others. Everyone else is finishing in May, and this program goes through August 2017 when we need to deliver for launch. So these gentlemen have decided to forego their graduation. They're going to stay here for, no? That's right. They're going to hand it off to the next student team. And so there's a couple of issues that are unique to this group in that they're only doing a portion of it, of the whole project. And there's also a pretty high risk we don't get the contract, okay, the award. It's a very, very, very competitive award, and this is our first time going up for it. So they've also had to simultaneously kind of plan a contingency for the unfortunate incident if we don't get the contract. So kind of keep that in mind as you listen to these gentlemen give you their talk.
Okay, so we are working on, as he stated before, the USIP SRFO NASA project, and that stands for the Undergraduate Student Instrument Project Student Flight Research Opportunity. We're going to be focusing on high bandwidth, high throughput, free space optical data transmission. We are personally concerned with finalizing the budgets, developing a prototype, as well as developing the system architecture. This is going to take place over the next 2 years. So as Dr. Boranek is back there now, as he stated before, we're going to pass it off to the following year's Capstone program. So now I'm going to hand it off to Beneath, and he's going to handle the purpose.
Hello, I'm Beneath, and I just wanted to point out the general purpose of the entire project as not the capstone itself, but rather as the school project, will be to plan and construct a satellite to be launched into geosynchronous orbit. This satellite has to have both RF communication abilities as well as laser communication, as it will be receiving light from a ground station located in the location of our choosing. Explicitly for our capstone objective, we're going to be researching the feasibility of the optics laser. Can it travel through free space without experiencing too much issues? Is the signal to noise ratio such that we can actually read whatever signal we're getting as distinct from the background radiation? The second thing we have to look at is the budget. We have a limited budget of $100,000, which seems like a lot, but a magnet orbiter costs about 35 grand, so not. We have to also look at specifications that are required, which includes anything from the amount of power that's required to is it durable enough to survive possibly the specks of dust that hit it as it is in orbit. And finally, we want to create a prototype of the laser such that we will test over a 2-kilometer range to see how much diffraction occurs based on the light that's being transmitted, as well as to see if there's any other issues that might come up with it. So, going back to what the requirements actually are, the first thing it has to do is detumble as soon as it's jettisoned from the NASA rocket that's been launched. So what we've been led to believe is that the CubeSat is a unit that will be jettisoned off of the rocket as soon as it's in space. And there's multiple units of these moving in different directions. The issue with this is the moment that it's launched, it's moving at any momentum. It could be spinning, it could be completely stationary. We don't know. All we know is it's going to be orbit. So we have to have sensors that will be able to tell whether it's actually in a correct position perpendicular to the Earth, such that you can communicate with the ground station, and as well as for the solar panels, because once they actually try to gain energy, they have to be in a very stable manner. Second requirement has to communicate with that ground station. As I've mentioned, through our communication as well, has to receive the laser uplink data. The size has to be within a specified limit that's based on the NASA requirements based given us. The budget, as I said, is $100,000. It must be self-powered. We will be including a battery in order to allow for the magnet torquer to work in tandem with it in order to allow for the detumbling process to occur, but the battery itself is meant only mostly for the detumbling process. It also has to meet FAA regulations. Whatever laser uplink we send can't interfere with communications that occur currently in America. And it has to be robust. It has to last at least a minimum of 2 years, up to 5 years, based on whatever the NASA project requirements would be. I'd like to now pass it off to Matt Fantino to talk about our specifications.
Hi guys, Matt Fantino here. I'm the hardware engineer in this project. Here are some specifications we have for our CubeSat. First thing is the cost budget. As you guys can imagine, space grade material is not cheap. So one thing we had to deal with was either a reaction wheel or a magnet torquer. A reaction wheel pretty much spins, and based on the torque and speed to detumble the thing after it shoots into orbit, it'll spin around and determine the position to keep it in low Earth orbit. Or the magnet torquer, which is what we had to pick because it's the cheaper option and to fit into our budget. That's what we had to choose. The magnet torquer pretty much uses the Earth's gravity to determine position and detumble the CubeSat. Size budget, we had either 3U or 2U, 30 centimeter by 10 by 10, or 20 centimeter 10 by 10. You can see over there, it looks like we're probably going to go with the 3U because in order to fit all that equipment, we're going to need a bigger box. And with that, we have a weight, so we need to keep it in weight constraints because the magnet torquer needs to actually physically be able to detumble this thing while it's spinning at whatever velocity it's spinning at. Here's the laser to camera communication. The camera we chose is a USB 3.0 camera that has small form factor, good field of view, good global shutter capabilities, and correlated double sampling. Pretty much CDS, which is correlated double sampling. It'll take 2 pictures, and from the reference voltage of the pixels in one picture, it will subtract that from the input voltage it has, and that will allow for higher sensitivity and higher dynamic range. When the laser comes in, you can see that we have the field of view of the camera. Laser comes into the lens, reflects off, scales it down so that the CMOS sensor can detect it, and it can be processed by the flight controller software of the microcontroller. We also have 2 filters that we use, an NIR bandpass filter, which what it does is it'll block the UV ray. It increases the photosensitivity of the diodes in the sensor, allowing for, because our range is 852 nanometers wavelength for near infrared. So in order to try to get a better reading on our laser with no false positives, that's what we use. Then we also have a cold mirror long pass filter. The cold mirror long pass filter will block out anything below and including a 700 nanometer range. So that includes UV light and the visible spectrum so that we can make sure that the camera sensor does not get damaged at all. Let me hand it over to Mike to do the ground station laser, please.
Hello students and faculty, my name is Michael Hall and I'll be talking about the ground station laser. So the main design parameters for our ground station laser is laser transmit power and beam divergence. Our laser will be operating on a near infrared spectrum of about 852 nanometers and will transmit a power of about 10 watts, which will be aimed through telescope, which will be transmitted through a telescope and aimed to a certain point so the camera sensor can receive. Our ground station tracking will begin as soon as launch begins, which will enable our onboard GPS to track the CubeSat with an ambiguity of 8 kilometers. Our GPS will also provide location fixes every 1 second intervals to track the CubeSat while it travels at 8 kilometers per second. Once a downlink communication is established and the downlink beacon has reached the ground station, the ground station will then respond with a confirmation packet on the radio uplink. Once this is received by the satellite will then respond with a telemetry information to the ground station. Once the satellite reaches the ground station will then use its location and time information to then predict time and angles once the CubeSat has sufficiently risen above the horizon. Once the CubeSat has risen above the horizon, the laser will fire. Now when the laser fires, there will be an estimated location of the satellite. When the laser is detected, our processor on board will then send location and time information down back on the radio downlink. As you see, there will be constant communication between our radio uplink and radio downlink. Now, while this continues to happen, our orbit model will be continuously refined as our CubeSat will receive laser hits. Our laser contains good correlation properties to minimize the possibility of false positives and false negatives, to reduce the chance, to reject unwanted signals such as sunlight. A dithering effect comes into play using a point spread function to scan a laser randomly over the ambiguity area. And as you see here in the diagram, we have our ground station stationed on the Earth and our satellite in the 8-kilometer ambiguity area. Success is measured by our ability to maintain the uplink while it is in its overhead orbit. So now moving on to potential pitfalls. So as potential pitfalls go, we can have financial drawbacks as a satellite could be too expensive to actually construct. There is also the possibility of a failure during launch, which could cause damage to the CubeSat components. Our EPS, our electrical power system, could cause low voltage levels and low current levels, which can also in turn cause a power failure. We are also using a battery which is used to keep the temperature above 0 degrees Celsius, for which if this falls below 0 degrees Celsius, there is also a chance of power failure. Our camera on board of the satellite is only connected via a USB, so it's not very secure enough to lock, which could loosen during its orbit. Shock and vibration from the launch could also make the camera inoperable. Now, for optical link closure, our laser beam could be spread too much, which would cause an insufficient signal-to-noise ratio. What this would mean is that we will be unable to decipher the real signal from the noisy signal. If we are unable to detect the signal, our beam spread angle and our dithering range must be adjusted to find an appropriate trade-off. Now, the most important pitfall here is the last one, which is timing desynchronization. Our ground and flight clocks must be synchronized post-launch, or else poor synchronization would cause a residual position ambiguity. What this would do is that this would reduce effectiveness and would force us to use a wider beam, which could cause us to compromise our optical link budget. If we are unable to overcome synchronization, we will then pursue an alternative mission of infrared imaging over the Earth. I will now bring back Beneath to discuss our backup.
So just for the record, in case the NASA project does not get approved by NASA from college, we do have a backup plan in which we would install a solar panel PV array on top of the rooftop of the parking structure across from Main Hall. Effectively, what we wanted to do was basically create an array, provide free energy to the school, hook it up to our power grid, green, everybody's happy. The one thing that I wanted to do explicitly to kind of make it a little bit different was that now, because of the inclusion of transparent solar panels in manufacturing processes, we can actually have solar PV arrays based on, they don't absorb the visible spectrum of light, they only absorb UV light. So effectively what that would do is that we can have a running biological study where the currently existing rooftop garden, we can observe how those plants grow with a lack of UV light. Which is, that's cool, in my opinion. And not only is it green, it also helps us utilize certain electrical engineering, computer engineering skills as well, which includes power management, power distribution, and also we have to meet industry standards, keeping safety in mind and making sure that everything runs as it should. I'd like to move on to the spring 2016 plan, and Alex Parisi.
So we're concerned with three things during the next semester, and that's the feasibility testing, which involves construction of the prototype. We're also going to have to begin development of the system architecture that's associated with this prototype. And before all of that actually occurs, we have to finalize our budgets. So this way we confirm part selection and size. Mainly this is impacted by the 3U versus 2U decision. I mean, that's going to have a large effect on the Form 8 budgets, weight, size, power, and cost. So once we have the prototype constructed, we can begin testing short-range free space optical data transmission. And the system architecture is going to have to be developed in parallel because we're going to have to be able to interpret the signals that we're actually transmitting. So we're also going to have to be concerned with the detumbling process because the final weight and budget calculations, the final weight budget calculations are going to impact how much energy we need to detumble. Once we graduate, we are going to pass this project along to future Capstone students. So we have scheduled it so that each kind of section per semester utilizes the physics, electrical engineering, and computer engineering departments. For example, in the fall 2017, students are concerned with the radio link development, the power profile, and the firmware. So we're going to utilize all three of these departments at the same time. Faculty consultation is also very important due to the scope and, I guess, nature of this project. Our two main contacts are Dr. Warren and Dr. Yakos, because they are so heavily involved in the construction of the proposal. Outside consultation is also going to be important, such as the mechanical engineering departments for the tumbling process and the construction of the CubeSat module. So in conclusion, this research can be used and adapted to smaller satellites such as other CubeSat projects that might be data intensive and have to transmit between other satellites or down to their own ground stations. The prototype could be developed further to actually include a transmitting laser on the satellite end as well, but that was way too expensive for our current budget. That could prove two-way free space optical data transmission, and then eventually this could be adapted to larger satellites and then change the way that larger satellites communicate with each other in their ground stations. So now we will open the floor to any questions.
Your backup program may be of concern if you don't include a lot of design components. ABET requires that design is an important feature of the process. So we must be careful for the backup that contains enough design. Yeah, it's very important.
So what kind of laser are you going to be using, at least for the preliminary test?
It's near infrared, so did you say it was E52?
Yeah.
Yes,
Just a comment. Thanks for the education. Before you just told me what you're doing with regard to satellites, I knew nothing. And also thanks for having a backup plan, because prior to you saying that you had a backup plan, Dr. Morrow asked me to take out my checkbook in case you didn't get funding. So I need to do that. Excellent job.
Thank you.
Thank you.
You can still take out your checkbook.
I get that comment a lot.
We could definitely use more than our 100K budget.
So do other schools that do get selected, I guess, do they have a budget that their school provides? That's not just NASA, so you're not bounded by
You
NASA
can, yeah. Some schools do contribute to the budgets, but the budget that we have is from NASA.
So that's why we want everybody to donate so we can all go to space.
Any other questions?
Do you guys know exactly when you're going to hear back?
Sometime over the spring. So
Sometime between mid-December and beginning of May.
thank you.
Just one quick question. For the motherboard and the processor, did you guys look into what's the word here, electronically hard chips, sets, and all that kind of stuff? Because I know once you get in space, you don't have the protection of the atmosphere and pretty much the whole magnetic field at Earth. So you can need gamma rays and X-rays just flying through space.
It's
You know,
radiation.
processor.
I'm not sure for like the motherboard or any of that. I'm sure it's probably shielded properly. It's space grade material, so I'm sure they kept that in mind. But I mean, as I mentioned, we also have that long pass filter, which is what is going to, for the camera sensor at least, it'll block out the visible spectrum and UV light and solar radiation and make it block all that destroy us.
Do you guys have something within inside the CubeSat that will help reposition itself? If you
Yeah, that's
need
the magnetometer. It does attitude adjustment.
So that does all the
adjustments.
adjustments.
Yeah. And Matt said before that we were looking into a reaction wheel, but it was like half the budget, so it was just not feasible at all. Anybody else?
I don't understand that thing. So how does it work? How do you stabilize it? I mean, you don't have little jets coming out or anything, right?
Magnetometer or the reaction wheel?
Whichever you're going to be
You're
using.
using the magnetometer.
Yeah.
Yeah, so it's like just a long coil of wire and it interacts and you pass current through it, which generates a magnetic field and that interacts with the Earth's magnetic field. So you can use that in combination with sorry, what were you saying?
So it orients?
Yeah, it's just using it for the Earth to orient itself, as well as, you pass current through it and that can use the Earth's magnetic field to adjust it.
Thank you.
Yeah, I'm really keen on learning about that.
It's definitely a
There's
complicated
actually
process.
a lot of intellectual property that comes when you buy that magnetometer, but it's a little bit magic.
It's a box.
settle?
There's a combination. I'll just speak to this issue right now. There's some coils integrated on some of the solar panels, right?
Yeah.
And so those are essentially the kind of the rotor of your electric motor. And but then the intellectual property comes in a processor. There's codes and for an FPGA that actually uses these coils also to sense, and it has other inputs in terms of the sensing the tumbling motions, and there's some algorithm. That's way beyond the scope of this Capstone project to develop that algorithm. It's a rather turnkey. So, yeah. Any other questions for the students here?
Bring Manhattan College to space.
I would like to recognize Dr. Yakos. It's his idea.